So today I'm going to show you a new way that your calculator can show motion. Because if we go, here's my concern. So suppose we go back to this problem right here, right? An object moves according to x of t equals this, right? What is that object doing? That object moves according to this. What is the object doing? That's the question I want to really examine now, and we're going to examine it using your book, page 137, problem number 20. And so I'm going to have you, before we do anything else, you're going to go to where the Google Classroom has all the videos, find Calculator Lab motion graphs. I think it just says motion lab. All right, and download that, and you're going to look at that. So it's going to refer to page 137, problem number 20, which I printed on here, but it's a little hard to read, so you might want to go to the textbook on the website. But it gives you a similar function to what I just showed you. So it uses s of t again, which they like to do. I guess that way, it doesn't matter whether it's x or y. Negative t cubed plus 7t squared minus 14t plus 8. So the question is really going to be, like, we have all these questions, but part D says describe the motion. We've been sort of avoiding that, and like, what does it look like when an object moves according to this? I mean, you know what this graph would look like. It would be a negative cubic, right? So we know it sort of looks like this. Like that, okay? But that's not what this object is doing, because when we think of a negative cubic that does that, one of the axes is time. And this object is going to be moving. I'm going to have my s of t in our graphs that we do is going to be actually the horizontal axis, the x-axis. So this object is going to be moving only back and forth. So actually an important idea from calculus is that when we talk about motion, in the first 2 semesters of calculus, which is what you're doing in BC, the motion can only be in one dimension. All right, so the motion can only be going back and forth on a line, okay? Or it could be, you could have a curvy track that something's going back and forth on. So, but as long as it only takes one number to say exactly where a particle is, because it's on a track, like think of a train or a road. So the road could go all over, but if I say you went 60 miles on that road, I know exactly where you are. That, by the way, is a case of a figure that is locally one-dimensional. So we only have one spatial dimension in all our calculus considerations of movement until you get to Calc 3. So the reason is you have a function, your position function is s of t. So s is your position and t is your time. That's 2 variables. So in the first 2 semesters of calculus, you'll only really be able to do derivatives with 2 variables. If you do more than 2 variables, so let's say we had an x and a y that both depend on t, all right, now for most things that we're doing, you're into what we call multivariate calculus, which normally is your 3rd semester in a university college course. You'll start doing calculus of functions of several variables. Instead of just s of t, it'd be s of, for example, x and y. Right. So now we're actually going to have ways to deal with x and y by dealing with them completely separately as 2 separate functions, where each of the functions x of t and y of t are themselves each only locally one-dimensional, and then we sort of put them together and create a parametrically 2-dimensional function. We'll get to all that. All right. My claim here is when we talk about motion in calculus, generally we're only going to be going on a figure that is locally one-dimensional, because we need 1 dimension for space and 1 dimension for time, and that's all the variables we got. A variable is a dimension. All right, so what I'd like you to do to start off is, with that in mind, things are only going to go back and forth in lines. They could go vertically, they could go horizontally, they could go back and forth along a track, but they're only going back and forth. They're not going all around, unless we pull some trick. All right, so with that in mind, we're going to download the Motion Lab, and I want you to just read through this carefully and see how much you can do of these first questions without coming back and looking at the videos. So at any point you get stuck, come and start going through the videos. I'm going to go through the first one in the video, but I'd like you to try and do it on your own first, and then you're going to be up to doing 21 and 22 of of the problems. And I put 21 and 22 here. And actually, by the way, just as a heads up, because I'm having you do sort of parts of each of these questions, the homework for this is going to be that same page 137, and we're going to do number 19 through 22 all. So I'm mentioning that now because in the lab you're going to do parts of that. So you want to sort of bear in mind organizationally how you'll be able to put it all back together at the end. Okay, so your first job, pull down this lab, pull out your calculator, and do this lab. And do as much of it as you can. Check in with the next video if you get stuck, or if you didn't get stuck and you just want to make sure you did it all right.